Hello and welcome to Bay College's Intermediate Algebra online lectures. This is a very exciting chapter because it's the last one of the semester if you're enrolled here at Bay College. This is section 9.5. It deals with systems of nonlinear equations. At some point in your algebra career you worked with systems of equations. I believe in chapter 5 we worked with graphing systems of inequalities, or actually that was chapter 3, 3.5 I believe. We had linear inequalities, so we graph them and we find their area. Well, we're actually going to look at systems of nonlinear equations because they're not always going to be nice straight lines. And as we've seen in the previous sections, we can have parabolas, we can have circles, ellipses, and hyperbolas. So the first method for solving nonlinear systems of equations is we're going to solve by graphing. Now the first two equations, this is my system. Find the point that these values intersect. That is the definition of solving a system of equations. Where do these two separate equations overlap? Where do they share common points? Now this here, if we look at it, the first thing we should always do is assess what the shape of the equation is. This is a parabola, y equals some x value squared. So I know it's a parabola, and it opens up because it's in terms of x, and that coefficient is positive. This one here, maybe you don't recognize this one. This is called an inverse function. It has the shape that looks like this. And I do believe for my students, this will probably be the first time you've seen this type of function. And it's called the inverse function. It is one of our library of functions or parent functions. Now, if I look at this and say, well, if they were to overlap, maybe I could have 3 values, maybe I could have 4 values, something of that nature. There are different solutions that could happen if I overlap these. So I know I can find some solutions, but what if they were totally separate? What if I had a parabola over here in this quadrant? Well, eventually they'd cross way up high. So this is the issue that we have with these systems of nonlinear equations. So we're going to solve by graphing. That's the first method. We're also going to look at substitution and elimination, which, trust me, are a lot better than having to graph some of these functions. So if I graph this value, it's a parabola. So if we do a little bit of work, we could put this in the standard form. We could find h and k, or maybe we want to use the vertex formula, negative b over 2a. So I can find that x value. I can plug it in, find the y value. I've already graphed it because, you know, that inverse function is actually pretty tough here for plotting points. It can get pretty ugly. So I found the vertex of my parabola. I found the intercepts of my parabola. And then I plotted a couple extra points using some symmetry of x equals 1 to find 2 more points. I found one of them and used symmetry for the other. So here I have my parabola. Then, just by choosing values for x and solving for y, I graphed part of my inverse function, this one right here. And then I plotted some more points just to make sure, you know, I didn't have anything else over here that was going to intersect. By definition, where these two graphs cross is the solution to our system. And if we graph those and look, this is the value x is -1 and y is 4. So by graphing it, this is what we get. Now it's really important, if we're going to do this by graphing, is that we have a very accurate graph. Because if it's just something we sketch in the margins, it's going to be really hard to determine, did I sketch this accurately enough to actually determine what that point is. Sketching by graphing, or solving a system by graphing, gives us an idea of where that point might be. That graph has to be very accurate. All right, let's look at another one that asks us to solve by graphing. I have 2 examples in this video because solving by graphing is usually, or at least from my perspective, much more difficult to get an exact answer. And that's our goal. So the first thing I'm going to do is I'm going to look at this and say, what type of equations am I dealing with? Well, here I have both x's and y's are squared. Well, that leaves either a circle, an ellipse, or a hyperbola. I see it's adding. And I notice, hey, these coefficients are different. I've just identified this as being an ellipse. It's an ellipse of some sort. Maybe it's stretched in x or maybe it's stretched in y, but I know it's an ellipse. I'm going to put this in standard form. X squared divided by 4, because I have to divide all these terms by 4. 4 over 4 is going to cancel. Just give me y squared equal to 1. We set it equal to 1. That's how we deal with these ellipses. And now I can determine my a and b. My a is plus or minus 2. Those values when squared gives me 4. I can think of that as being over 1. So my b value is plus or minus 1. And now I can go ahead and say I can put it on the graph now. I'm going to go plus or minus 2 in the x direction, positive 2, negative 2. Because it is centered at the origin, there is no h and k values. And I can go up 1 and down 1. Up 1 and down 1 from its center at the origin. And now I can graph that ellipse. And now notice, not too steady of a hand because it ain't a linear equation, right? So hopefully I graphed it close enough that when I graph this piece, I know that I'm going to have a solution somewhere in the general area. Now, let's identify this. The y value isn't squared or anything like that. It's just y to the first power, x to the first power. I've identified this as some linear equation. Maybe it has a positive slope. Maybe it has a negative slope. Let's put this into standard form. And I'll do that right here. I'm just going to rearrange this, put the x term out front, and divide everything by 2. So I get y equals negative 1/2 x plus 6. Here's my equation. I can graph this easy enough. I know the y-intercept is 6, so I'm going to go over to my graph and go 1, 2, 3, 4, 5, 6. And we can use the slope. I can go down 1 and over 2. So from this point, I'm going to go down 1 and over 2. And I can go down 1 and over 2 more. And I can go down 1 and then continue that, but we notice we have enough values to do that. Well, what does this mean? To solve a system, we're looking for the point in which they intersect. Now, they could have intersected in 2 places, so maybe I wanted to find 2 solutions. They could have intersected in just 1 place. Maybe I wanted to find 1 solution. But if I put it on the graph, I can see, you know what? They don't intersect at all. So where do they intersect? Nowhere. There is no solution to this system. So I can write it is a null set. There is no solution. No solution to this because they have no intersection. So in a case like this, it's easy to see that, yep, there's a big space in between them. They don't intersect. But in like our previous example, we can see, hey, some of these are complicated to graph. And maybe if our graph is accurate, we can find that solution. All right, let's look at this. We're going to solve this one by a different method, a method that we should be familiar with, something we've worked with before when solving systems of linear equations. We can use substitution. The first thing you want to do is just assess this. I look at this and say, hey, this is a parabola. Only one of my variables is squared, and it's the x squared, so I know it opens either up or down. I could put this in the standard form, and I'll just sketch that real quick right here. Y equals negative x squared. That's a parabola that opens down. All right? And I can tell h is 0 and k is 5, so I'm ready to graph that if that were the case. If I look at this, I can say, all right, well, this is a circle centered at the origin with a radius of 5. So identify your circles. And if I look at this, I could have at most 1, 2, 3, 4 solutions. But I might only have 3 solutions. 1, 2, 3. I could have 2 solutions. 1, 2. I could have just 1 solution if it went like that. And I could have no solutions if they do not intersect. So I know at most I'm looking for 4 solutions. I might find less than that, but that's okay. So what we could do is substitution. If we assess this, is there a variable that's really easy to solve for? Well, I've already done that here. I said, hey, this is a parabola. I can solve it for y. Y equals negative x squared plus 5. We can do a substitution. Take this value, solved for y, and substitute it in for y. If y is this value, put that value in. Negative x squared plus 5 is the same thing as y. So we put it into the equation, and now we have it. And now I can just FOIL this out. And negative x squared times negative x squared is going to give me positive x to the 4th. Negative x squared times 5 twice is going to give me negative 10x squared. And 5 times 5 is 25. Now we can do a little bit of simplification. Hey, I can subtract 25 from both sides, get this set equal to 0. I have x to the 4th minus 9x equals 0. And now I can solve this, can I? Oh.
Your 9x should be in x squared.
Oh, x squared. Thank you. Thank you very much. All right. Now I can factor out an x squared. And that leaves me with x squared minus 9. And I could factor it a little further. I'm going to go over here and say, OK, x squared minus 9 is the difference of squares. So it's x plus 3 and x minus 3 equals 0. And now I can say, OK, what are my values of x? Just use the zero value theorem. 0 times anything is 0. What would make this 0? If x was 0. What would make this quantity 0? If x is negative 3. And what makes this quantity 0 is the x positive 3. So I have 0, negative 3, and 3. Well, here's the concept here. I found 3 values of x. Chances are I'm going to find 3 solutions to this system. And now I can take those values for x, and I can plug them back into this one. It's already solved for y. I'm just using a little bit of assessment, saying this is going to be easy to find if I plug my values of x in. If I plug 0 in for x, well, 0 squared is 0, minus 0 is nothing, plus 5. So one of my points would be 0 and positive 5. If I plug negative 3 into here, negative 3 squared is 9. Negative 9 plus 5 is negative 4. Well, what if I put in the positive value of 3? 3 squared is 9. Negative 9 plus 5 is 4. Negative 4, excuse me. So I have these 3 solutions. To check my work, since I use this equation to find my y's, I can plug both x and y values into here and make sure this is a true statement. So I'll use the first value, 0 and 5. Well, 0 squared, 5 squared is 25. I know that is a solution. If I use negative 3 and negative 4, negative 3 squared is 9. Negative 4 squared is 16. 9 plus 16 is, in fact, 25. And the other value, 3 and negative 4, also works. 3 squared is 9. Negative 4 squared is 16. 9 plus 16 is 25. I know all 3 solutions work for this equation. And if I go back to my little sketches here of circles and parabolas, I can say, you know what? If I were to graph it, it would look just like this. But no need to graph it, because we can solve algebraically. And using the ability to plug these in and check, I know that all 3 of these values are solutions to this system. Let's look at another way to solve by elimination. Elimination is a little bit different than substitution. We're going to get the same results. But when it comes to elimination, what we want to do is find a value that we can, a factor that we can multiply through so that our y's or x's have the same but opposite coefficient, so we can add them together. It's also called the addition method. The first thing I want to do is, again, recognize what type of equations I have here. I see that subtraction of squared terms. I know this is a hyperbola. If I divided through by 15 and put it into standard form, get it equal to 1, I'd see, whoa, these coefficients are not nice. This, my a term would be plus or minus the square root of 3, and my b term is just a nasty number. Let's just leave it at that. So I wouldn't want to graph this, because it would not be kind to graph. So what I'm going to do is I'm going to say, OK, I've identified it as a hyperbola that opens in the x direction. So I'm just going to, on the margins, write a little sketch. It should look something like that. And if I look at this, well, this is the equation of an ellipse. And I've identified that because I see both terms are squared, but x and y have different coefficients. So I could divide through by 12, and I could find what A and B are, and we'd find that B in this case for the y value would be plus or minus 2, because the 4 would be in our denominator. Well, that's not so bad. But this one would be plus or minus 3. Well, I don't want to, or excuse me, plus or minus the square root of 3. I don't want to deal with a square root. So I just recognize that, yep, this is an ellipse of some sort. Now, if I combine the two, I might have 4 solutions. I might have 3 solutions, 2 solutions, 1 solution, or possibly no solution. So instead of drawing all those, just to give you the idea of the concept. Now, because they're not nice to graph, I definitely wouldn't want to graph these. So I'm going to use elimination. I'm going to say, what can I do to this equation? Well, the first thing I want to do is line up my x's and y's. I'm just going to switch the order of my x and y terms here. I'm going to rewrite the top equation. And just change the order so that my x's line up. If I tried to do elimination here, hey, they have the same coefficient of opposite sign. They're not the same terms, so that wouldn't work. So I'm just going to change the order. And now I could say, all right, now we're ready to say, what can I do? If I want to eliminate the x's, I'd have to multiply this one by either negative 4, so this would be negative 20. And this one by positive 5, so this would be positive 20, and then I could eliminate the x's. But I'm going to choose to get rid of the y's first because they have smaller coefficients. I prefer to work with smaller numbers. So what I'm going to do here is I'm going to multiply this one by 3 because it's already negative, and this one by 4, so I don't have to worry about that sign. They already have opposite signs. I just have to make the coefficients the same now. So I'm going to multiply this one by 3 and multiply this equation by 4, and I'm going to take it over here where we have more board space. If I distribute that 3 through, I'm going to get 15x squared minus 12y squared equals 45. Then I'm going to distribute the 4 through the other equation. I get 16x squared plus 12y squared equals 48. Now, elimination is called the addition method because I'm going to combine these two equations by adding them. 15x squared and 16x squared is 31x squared. Negative 12y squared and positive 12y squared. Hey, we don't have to worry about y squared anymore. We've actually eliminated it. And then 45 and 48 is going to give me 93. All right, well, that's actually good news because 31 and 93, even though initially we might say, oh, those aren't nice numbers. Well, if we do the division, I get x squared equals plus or minus 3. 31 goes into 93 3 times. And then I could say, OK, I can, oh, plus or minus. I'm jumping ahead of myself. I haven't introduced that square root yet. X squared is 3. So if I take the square root, x equals plus or minus the square root of 3. Now, we might look at this initially and say, wow, plus or minus 3, or square root of 3, we're dealing with an irrational number. Oof, I don't know if I want to find those values. Honestly, it's not going to be so bad. Leave it as a radical. We found some x values. Let's go find some y values. How can we do that? Well, let's go back to our original equations. I know one of the x values, so I'm just going to plug it in here. The square root of 3. Well, if I square the square root of 3, doesn't matter if it's positive or negative, those conjugate terms, the square root of 3 squared is 3. 3 times 5 is 15. If I subtract 15 from both sides, I get 0. Negative 4 times something equals 0. That tells me that y is 0. So I solved for it, and I actually didn't have to do any math. It was a little bit of mental work. So I get the square root of 3 and 0. And if I put the negative in, its conjugate, I'm going to end up getting the same result. So I found 2 values, and they just happen to be, if you recall, if I said, well, if we adjusted this, I'd find that plus or minus the square root of 3 for that ellipse. Well, I also would find that plus or minus square root of 3 for that hyperbola. This is the solution, and I can check my work by plugging it back in and finding, yep, if I square this value and multiply it by its coefficient, and if I square this value, real easy because it's 0, I'll end up finding a true statement. So both of these will work if we go back and check them. And it's not that hard. If we square a square root, we know that it just eliminates itself. So we can work with that. All right, so this has been the very last section of intermediate algebra here at Bay College, section 9.5. Thank you for watching.